My name is Cedric, and the general problem that we are facing is trying to use the 7-segment display on the FPGA board. So, a couple things to know about the 7-segment display on the FPGA board is that it comes with four different 7-segment displays like blocks, right? So we would have and 0 and 1 and 2 and 3 because each of these are the 7-segment displays respective anodes. All right. And so capitalizing on that, we would then want to make sure that for whichever anode we are utilizing, um, it is going to have a display at that specific anode. So first things first, we know our several inputs that we're going to have for the system. We know that we're going to have a clock and a reset. We know it's going to be a clock because we know it's going to be depending on any sort of input that we put into the system. We know that it's going to be depending on a in a sense a sequential pattern, such as whenever there is it senses a pause edge of a signal, then it's going to be requesting for any sort of feedback, which is in a sense what the flip-flop does, right? Anytime it is pause edge or neg edge, right? It is going to um, give out whatever result is represented in the general system, right? Uh, but anyway, so we know we would have a clock and a reset, right? And then we also know that we're gonna be displaying each of the anodes in 4 bits, okay? And we're doing 4 bits so that we can represent it in all the values in hex, right? If we wanted to, right? Which would that would be from 0 to 9 and then A through F, right? Um, where um, where A through F is representing the decimal values of 10 to 15, right? And so we know that that's gonna be 4 bits, and so then we're gonna represent these 4 bits to the respective anodes, which is hex 0, hex 1, hex 2, hex 3. And then we have each of the respective anodes has the respective decimal point. So we're gonna have a 4-bit for that. And then we also know that we're gonna have we have four different anode blocks, um, and so it's gonna be 4 bits. Where uh, for those anode blocks, uh, each bit is gonna represent one of the 4 blocks, right? And then of course we know we have our 7-segment display, but this 7-segment display is going to be capitalized as 8 bits because that most significant bit is going to be represented as the decimal point, right? And that will be brought up later, right? So that's how we broke up our inputs and outputs of like what we're going to be using. But now it's going to be like how are we going to be organizing that information, right? So we decided to come up with using an 18-bit system, right? Where where we would have uh, where we would have to start with how are we gonna be displaying it so that like we are able to see um, how often uh, the values are being represented on the 7-segment display, right? Because if it's too flickering too fast, then we wouldn't be able to see it. So we need to we need to have a certain refresh rate so that we would be able to see it when represented in the FPGA. So we would be utilizing a flip-flop where we would have a counter flip-flop system, right? Um, so then we would have uh, our um, our current state register, and then we would have our next state here. So this would be from 0 to 17. This is 18-bit, and this is another 18-bit. And so here is the counter. So these are the terms that we're going to be using for the counter, right? And then this would be hex in. Well, because we do have 4 different hexes, right? So whichever it is being called on, it will be used, right? But we know that we're going to be utilizing 4 bits, so that's going to be our register here, our reg here. And then, of course, if we wanted to use the decimal point, then we know it's going to be represented as 1 bit, so we have reg here. And something that we'd have to also realize is that the reason why qreg, hex in, and dp are regs because these are states that are gonna hold if we wanted to hold them, right? Um, we're gonna store these values as long as we want to do so, right? While for qnext, this is a state that is not gonna remain constant. It's gonna change depending on uh, qreg, right? So there's no actual value being stored for an X amount of time because qnext is depending on qreg, right? Which is what we would show here, right? We're assigning that qnext is going to be qreg plus 1, right? So this is going to be assisting with our counter here. So that's why we assign qnext here as our counting process. And so we would then be using an always block to create a system where we're able to access reset, right? So then we would be using a non-blocking system, right? So that would mean that whenever possible, whenever it is a pause edge clock uh, or a pause edge reset, then we're able to reset and make it qreg equal to 0, right? And then if there's no any sort of reset, then we're gonna just keep on counting using this qnext assignment here, which will just be our counter. So this is our simple counter here. And so now it goes on here where, okay, so we know that we have an 18-bit system, right? But we also know that of our 18 bits, the 2 most significant bits are going to be used for uh, our mux, the select input for our mux, right? So depending on the results of from like 0, 0, 0, 1, 1, 0, or 1, 1, then depending on the 18 and 17 bit, right? Then it's gonna represent on like which anode it's gonna be represented on, and then from there it's gonna then depend on which hex we're depending on as well, which hex value we're depending on here. So we also have to keep in mind that when creating this design here, we know that it's going to be an active low, meaning that when it is a low value for that certain bit, that means it's going to be on, it's going to be active, right? So in this case, 110, 0, that is the least significant bit operating for an and 0, the anode 0. So of course, going back to here, we know that this would be the one displaying. and this would be off, this would be off, and this would be off, right? And then from having here dpn 0, looking at the 0th bit, then that would mean that we can configure this decimal point here if we wanted to, right? And so the same is being represented into the other ones, right? When depending on those two most significant bits, then we would be looking into the second anode block and then the third anode block. And again, it is active low. And we in this case block, we would have to also make sure that we have some safety precautions so that there is no weird behavior when implementing, right? So we made sure that there is no decimal point. Hexen is going to be just 0. Um, and all the anodes blocks are going to be displaying nothing, right? So they're all going to be set to low. Okay. And so stepping aside from that, now it's questioning how are we going to be representing the bits uh, for the 7-segment display, right? So we know when we're representing the 7-segment display, we know, well, out of the 8 bits, it's the 7 of them are going to be pertaining for the cathodes within that anode block, right? So from here, again, knowing that we're going to be using the active low system, we know that when capitalizing on the 7 bits, we are going to be having where if we wanted to do 0, then these are all going to be on except for our G, right? Um, so yeah, so when we're talking about 0, so that means that since this is going to be our 7th bit, we're going to expect only our last bit to be 1, right? If we want to display 0, right? And so that's what we have here. We have our last bit here, or to make it more straightforward, our least significant bit. Our least significant bit is going to be 1 there. And so if we wanted to display, let's say, because we would be representing 15 different digits, so we're going to do a few examples here. If we wanted to display A, A, right? So we would be expecting E, F, A, B, C to be on, and then um, G would also have to be on. But D is the only one that is not going to be on. This one's going to be off. So we're going to be expecting D to be off, right? So going back, for A, this is A, B, C, D. We said D wanted to be off, so that one's going to be off, right? So knowing that from how the 7-segment cathodes are being laid out, and we know that we're having um, this active low system, then we operate on such. Um, And so knowing that we're working with those 7 bits, right? We know that those 7 bits are going to be corresponding to a hexadecimal value here, right? So whatever hexadecimal value we call upon here, it is going to be corresponding to these 8 bits, right? Which is going to be allowing whichever cathode to turn on or off, right? To display whatever we wish to display, right? So yeah, and so that would mean that whichever hex in um, from here, uh, whichever hexen would be able to operate their um, their 4 bits to allow the 8 bits to configure what we wish to configure onto the on the 7-segment display, right? And so this eighth bit here is the where it is assigned to DP here, right? Um, which of course also depends on whichever case we have here, right? And so looking into our TB, our test bench, the way we have it here is again we have our anode and our 7 segment, right? These are both outputs, so we're gonna classify them as wires. And then we also know, again, these are our inputs. So these are registers because they're going to be held at a constant state as long as we say that we want them for. All right. And then here we are just referencing our test bench variables to that of the main module variables here, right? And then here we have a period of 10 nanoseconds, right? So with this period of 10 nanoseconds, we pretty much have our clock here, um, which gives us the frequency of 100 megahertz. So with this 100 megahertz, we would be able to create a clock that constantly goes down every 5 seconds and constantly goes up every 5 nanoseconds. Okay. And then here we would then have our several tests that we'd be referencing through the behavioral simulation, right? All right, so looking into this behavioral simulation, right? We would showing that it fits within our test bench, we would first active set our reset and make sure that there's no configured decimal point. And after another 20 nanoseconds, we would then release this reset, right? And so after another 100 nanoseconds, we would then want to have the hexadecimal value of 2 onto the 7-segment display. So let's see if that has been true, right? So uh, at 20 nanoseconds, we have it on. We have reset on. So we do have it on here at about 20 nanoseconds. And so it's on, and then reset is going to go off here at another 20 nanoseconds, which is 40 nanoseconds, showing there. And so then it's going to be off, and then after 100 nanoseconds, so we should be looking at about a 140. So at 140 nanoseconds here, we have val 0. That should be displaying the hexadecimal value of 2, right? Which does show to be here, this hexadecimal value of 2, right? And then for val 1, we then would have 4, right? Now, before we get this hexadecimal value 4, we got 0 for value 0 here for this term, right? So that's what happens after another 100 nanoseconds, which should be at 240 nanoseconds, right? So at 240 nanoseconds, right, we do receive 0 for value 0, and then we do receive 4, the hexadecimal value of 4 for value 1 position. And so it is then going to become 0 again for value 1. And then it's going to become 6 at about 340, right? See if we can show it. Let's see if I can do this. Okay, actually that should be better. All right, so we were looking at here, right, at 340. At 340, val 1 is at 0. It does become to be appear to be 0 here. And then at val 2, it starts to appear to be 6 for hex, in hex, for val 2, right, which is what we see here. And then after another 100 nanoseconds, which should be at 440, oh, 440, then that is where then we would receive the signal for the hexadecimal value of 7, which we have here. And of course, value 2 is now going to be set to the value of 0 in hex, which is seen right here. And then value 3 is going to be set to 0 after the value of 7, right? Where then after 0, for after 100 nanoseconds, it is then going to be represented as F, right? Which would be seeing that at around 640 nanoseconds. So this is what we exactly want. This is exactly what we wanted here. And then we see here that we're in the state for the most significant bits where it is going to be displaying on the first anode, right? So this is exactly what we want. We want to make sure that we're displaying for this first anode here. Uh, the thing is that when representing it into the FPGA board, even though I represented val 2 and val 3, and also val 1, realistically we would not have actually seen those values, but we know that those signals are active, right? The only one that would actually be represented if we were to represent this into the FPGA board would be and 0, because look, this and 0 is active as it is low. So because we're dealing with the active low system. So since it is low for this whole entirety, for this program as it is going on, we know that is going to be displaying for that anode 0, right? While all these anode 1, 2, and 3 are going to be off for the whole entirety. But again, even though these 3 would not be functioning, um, again, we know that the signals are going through and they're processing correctly in our system. So we verified that it actually works properly within our system, and generally how it is operating, it looks pretty good. Unfortunately, I cannot display it on the FPGA board just because of how much switches are being utilized, right? We're dealing with 16 bits. We're dealing with hex 0, hex 1, hex 2, hex 3, right? That's already, each of those hexadecimal values are 4 bits. So that's already 16 bits, right? Um, and we only have a total of 16 inputs for our FPGA board, which is unfortunate because even though it seems like that this for our constraint file, um, we do have a clock port. It seems like this is internal, so that might not be the biggest issue. But one of my biggest issues here was that I wasn't able to configure my reset port. I had tried to, but it didn't um, operate properly, right? So that is unfortunate. But because of this, I was not able to implement it to the FPGA board because there just wasn't enough inputs for me to actually test out with, right? And it's not like I can just simply remove this from the constraint file because then it's going to be the program and Verilog is basically questioning like, hey, where is this input that you declared? Like, we cannot get a bit stream just because you didn't state it in the constraint file. So I can't just put it because there's no more inputs. Um, so that was a huge issue that I had. But other than that, of course, each of the bits for hex 0, 1, 2, and 3 Each of their 4 bits would be represented for the switches and the buttons that are being supplied into the FPGA board. And then in this constraint file, then we would be putting eight um, our 8 bits that are being shown on the 7-segment display, and then including the decimal point would be appearing here, right, in this part of the constraint file. And then of course these anodes are representing on with which of the anode blocks are we going to be utilizing, right? Um, so yes, so the general problem was that there just wasn't enough inputs for us um, to actually successfully carry along a bit stream. So how did what did I learn from this assignment? Well, there's actually a plentiful amount of things that I actually learned from this assignment. I got to know more better of the syntax that is being utilized. I got I got to understand how how we would be able to use the 7-segment display, even though I wasn't able to actually use it on the FPGA board yet. Um, at least I actually got a feel to how the process that would be done in order to actually do it. Um, and then it was interesting too to implement a counter so that we could operate it into our refresh rate, right? Um, which is indeed needed. Um, and another thing that I learned um, was how these each of these 7 bits were corresponding to that of the 7-segment display, and how these 7 bits corresponded to a set's hexadecimal value, right? For our like decoder, right? Um, I thought that was pretty cool to implement. And yeah, that's pretty much mainly what I've learned. But even though unfortunately I was not able to implement it into the FPGA board, it seems like the behavioral simulation works properly. So yeah, I would say that for the most part, the lab was successful.